Hello, in this video we're going to construct a very primitive survey instrument and show that you can do real-life trigonometry with it. For this activity, you're going to need a couple of things, very cheap things. You're going to need a ruler, could be a meter stick. It just has to have a definite length. Like the reason I chose this ruler is because A, I didn't have a meter stick, ladies and gentlemen, and I did have a ruler of a definite length. This is 12 inches, and it's hard to see from the camera, but that these inches are marked. All right. The next thing you're going to need is a leveling device, something like this. You don't need anything this complex. Really, you just need that one level, but something with a bubble in it that you can tell whether the instrument you're constructing is level, ladies and gentlemen, with the ground. And this helps. There are ways of improvising without any of these objects, but this helps. This is a protractor with an arm on it that will move back and forth. And then you need something to stick it all together. Glue, hot glue would work. Tape would work. I'm using these little fasteners made by Scotch. Here's the package, Scotch multi-purpose fasteners. They're essentially small Velcro circles. So let's put it together. And oh, finally, you need a sighting. You need one last piece, one last instrument. You need a sighting scope. Now, I used a straw, ladies and gentlemen. I found this straw in the parking lot. All right, I didn't even clean it. I use this to look through to find the thing that I'm looking at. So what we're going to construct is a survey tool. And once you construct a survey tool, you can do actual trigonometry with it. So let's build it. Let me zoom out on the camera, and then let's build it. And from that build, we will be able to see how to do real trigonometry. Let me just zoom out a little bit. All right, so you can see what I'm building. All of these materials I had around the house. If I had a meter stick, I would have replaced this with a meter stick, but the meter stick is currently right here. It's supporting the camera, so I had to use what I had, ladies and gentlemen. I'm a teacher on a very minimal budget, so I had to use what I had. So take your ruler, and what you're going to do is place one of your circular sticky fasteners on the ruler. And then on that sticky fastener, what you're going to do is look at the markings on the ruler and place the protractor on the ruler perpendicular to it. So it's just at 90 degrees. Just at 90 degrees. And you can adjust this a little bit as needed. Get it to where it is exactly perpendicular to that ruler. Okay? Now you need to mount your level to the back of your instrument. So we're almost there, but most survey instruments, most survey tools have a tripod mount, but we don't have a tripod. I don't have a tripod, so I'm using what I have. This is a ruler. It's very thin, so we need a level on it to make sure that we're getting good measurements. So we're going to mount our level kind of right there, about right there, so we can read this bubble and see where it's level. We're looking for that bubble to be level. Okay, so I want it to, that's when I know when it's in the middle of those two lines, that's when I know it's level to the ground. So I'm going to place some Velcro here and one more Velcro down, maybe down here. I just have this in my trunk. You could use whatever you have around the house. So it's a very crude instrument, but the level will go there, and you just want to make sure that this level is lined up with the ruler. All right? That way when you're holding it upright, it will, when you're holding the this whole instrument upright, it will correctly show that you're level with the ground. Okay? So here's our instrument. And when we get it all fitted together, like that, we need to add the sighting scope. All right, so the sighting scope, the reason I like this straw is because it has a line. It's going to let me align very carefully. So as I'm turning this whole instrument, if I turn this here, the sighting scope will go with it. So when I look through the sighting scope, I'm actually turning this arm and I can read off the angle. So that's what I want to do. Let me just get everything in place. I'm doing this video after the fact, so I already built this thing and took it apart, so the sticky part of this is coming undone, but that's okay. So this goes on the actual armature itself. Put that there. And what we're going to do is put we're going to call this the sighting scope or the straw, right on the armature, and we're going to align it with the armature of the protractor such that it is exactly in line with that armature. So that way when we look through the straw at whatever we're trying to sight the height of, we move the armature with it like this, it will move with the protractor, okay? That's what we want. Okay, so this is essentially our whole instrument constructed. And it's very crude, ladies and gentlemen, but I purport that it will work. So there's your survey tool. All right, you've got a 1 foot tall ruler with a sighting scope on top attached to a protractor that can sight angles, and what you're going to do is look through this end and spot whatever it is you're looking for out the other end of the straw. And you're going to make sure that when you do that, you're going to make sure it's level. By when you hold this thing upright vertically, you'll see that the level is off balance. You'll get it to where it's just right, and then you'll sight again. And when you get the thing you're looking for in frame, then you will know. You just read the angle off the protractor, and you can do simple trigonometry to find out how high that thing is up. So when you get this instrument in the field, the way you use it, let me move this out of the way now. Very cool instrument. I think it's neat that we can build this with no money at all. We can do trigonometry, and we're going to see that we're actually very accurate with an instrument like this. Put it over here. The last thing you need is to figure out how exactly you're going to do this. So when you are trying to locate the height of something, that's what we're going to do in this example, you have to know at least the distance you are from that object. Now, you could use an expensive, lengthy tape measure or some kind of highly advanced laser equipment, or, ladies and gentlemen, you could use something as simple as a shoe. Okay, this is my shoe. I just took it off my foot. All right, now this shoe, if I bring my instrument back here, you won't be able to see the whole thing, but you'll see the end of it. That says 12 at the end. This is a 12-inch ruler. If I place my shoe on the ruler, I cover up the whole ruler, and if I slide this back a little bit, you'll see the ruler peeking through. It's just about, this shoe is almost exactly 12 inches. You know, I wear a size 12 or 13 shoe, but this shoe itself is 12 inches. So the shoe becomes a unit of measure. Now that's critical, because what I'm going to do, ladies and gentlemen, in order to sight the height of an object that I've placed on a wall that I don't know the height of, is I'm going to put my back to the wall, and it's a very crude way to measure, but it works. And I go heel to toe, heel to toe, heel to toe. All right, I'll show you what I did just so it's very clear. Take both shoes off now and show you what I did. I go heel, heel to toe, and just go back and forth like that until I cover the whole distance that I'm wanting to measure. Now I paced off in my example 10 paces. I put my heel to my toe 10 times, and that way I got 10 feet from the point on the wall. If I put my back to the wall really straight, and then I marched off 10 paces, that would be my distance from the wall, okay? And then this instrument comes into play. So when I got 10 paces from the wall, I put this instrument upright, straight upright, like this. I don't know if you can see this in that small camera, but I put this instrument upright like this, and I sighted my point on the wall by looking through. Look in the bottom left of your image right now. By looking through the hole in the straw to sight the thing on the wall I was looking for. All right? So once I got that in frame, inside my straw, I could see the dot on the wall through my straw. I knew that the angle that I was looking at the dot from was the angle to the floor behind me. So here's the other critical piece of information. And once you see the mathematics, it'll become clear. So you have, with this device, two triangles that you're constructing. You're constructing a triangle that is 12 inches off the ground, and this distance from here to the wall is 10 paces or 10 feet. And the angle you're making to the wall, in my case, it was 27 degrees. So it was something like that, 27 degrees. And there is a triangle that comes behind this instrument. So you have the triangle that you measured, all right, 10 paces from the wall. But then you have the triangle of the instrument itself. It's hard to show it all in frame. I'm just trying. You have the triangle formed by the end of the straw that goes all the way to the floor, and the height of that triangle is 12 inches. It's the length, or the height rather, of the thing that you are holding up to sight your measurements through, okay, like this. That height, this height, 12 inches. So if you had used a meter stick, your height for that smaller triangle would be 1 meter, okay? So in this case, I'm using a ruler of 12 inches, so that was my height. Now, let me show you what I found. So first, if I could, I'm going to load up an image that I took that will show you what I found when I found my image. Let me just look for it really quickly. All right, I'm going to show this on my screen. So here's what I was looking for. There is a dot in this image. I don't know if my mouse is showing for you, but that dot right there. Now, you'll see as when we get to the end, that was 6.25 feet off the ground. And I marched. I'm taking this photo from where I sighted through my sighting scope, through the sighting scope here. Okay, I was 10 paces away, and I looked through this until I saw that dot on the wall. That's what I did with this. And I found that my angle that I needed to turn my protractor armature to was 27 degrees off the horizontal. And I kept checking. It was hard. I kept checking the level to make sure I was level with the ground. And then I looked again and adjusted slightly, and then made sure I was level with the ground and adjusted slightly. All right, so it took a couple of minutes because ideally I would have had a tripod, but I only had that stick. All right, well, I claim that this works, and we'll see that it does. So this is what I was measuring. I was trying to find that red dot on my wall. I just stuck it up there randomly on the wall so I'd have something to look for. I measured off, I put my back to the wall, to that wall, and I marched off toward where I'm taking the photo from, and I shot that photo from the ground about where I sighted the image, about a foot off the ground. That's what I was looking at through my spotting scope. Okay? So let me get rid of this image and get back to our workspace. Now I'm going to zoom in on this workspace because we're going to do some trigonometry. I just have to zoom in on this workspace and we can start computing things. All right, that'll work. Okay, first let's model what we saw in reality just so we don't get lost in a blur of details. Okay, here's another protractor with an armature. We're going to do our cheater method here and use this protractor with an armature. So I need a pencil and the protractor with an armature. Follow closely. So there's 20 degrees marked on the protractor. So I measured 27 in the field when I did my field measurement. So what I do is I go up to 25, 26, 27. So I'm going to rotate this armature up to 25, 26, 27. That's what I'm going to do. So now this armature is at 27 degrees. Okay? So here's what you do. Take your pencil. There's a little hole right there in that, right there. So you put a little dot. Twist your pencil around so it makes a firm dot. Then mark off a line. See how there's a hole in here so you can draw? That's what it's for, is so you can mark off a line. And there's the dot. I need one other thing just to make sure it's straight. There are, I don't know if you can see them, there are scoring lines right here, so you find what even is. So you put a little dot next to one of them, like that. And when you take it away, you've got two dots that form a horizontal axis, and there's your 27 degree line. So here's how this works. Form yourself a little construction line, just like that, and then make a triangle here by connecting that with your origin point. And then what you're going to do, we can make this triangle a little bit bigger so it's visually. All right. Then make a right angle to the page. Okay. If you really wanted to do this correctly, you could do it like this. Flip this sucker up to 90 degrees. Draw it in like that. All right, so there's your 90 degree angle. Come down here. So now this is 90 degrees, and what we saw in the field was that this was 27 degrees. Well, the internal angles of a triangle add up to 90. So 180 minus 27, ladies and gentlemen, equals 63. So we're going to need this other angle here, 63 degrees. But that's not where the experiment stops. Let me erase this for a moment. Because this point right here was where my eye was. This is where my eye was, right? This is where I was looking through the scope, right? But my eye was 12 inches off the ground. That protractor was 12 inches off the ground. So there's another triangle we need to construct. We need to construct yet another triangle. So I'm going to do it like this. There's another triangle we need to construct. All right, so I'm going to draw a vertical line down. This line is going to represent 12 inches. All right, so it really, what I need now is 27 degrees again. we're exploiting a theorem of geometry, basic geometry, that says that the similar angles are the same, or the lines that are parallel have similar angles. So here's what we're doing. Let me draw it first, it'll become clear. Let me find 27 degrees again on my protractor. Okay, that's 25, 26, 27. 27 degrees. Okay, so now I'm going to construct another triangle. You see how I'm getting that? Do you see the line inside? It's all lined up. So I'm going to draw another point here inside the middle of the protractor armature to mark off my point. I'm going to put a little dash here so I know how to make a horizontal. Go back here, make your horizontal line. Okay, now just all you need to do is line up these lines here and basically connect the dots. All right, so but you have two triangles. That's the key point. At the end, you're going to have to add these heights. So that's also a right angle. Now this point down here is also 27 degrees. So my eye is right here. My eyeball is 12 inches or 1 foot off the floor. So this is going to be 1 foot. That's the height of this small triangle. Okay, now I don't know this height. That's what I want to know. I don't know that height. That's what I want to know. However, ladies and gentlemen, I do know the distance here. This was 10 feet or 10 paces, right? And we measured my shoe. My shoe was 12 inches in a foot. So this was 10 feet. It was crude, it was an approximation, but as you'll see, it's going to be pretty darn accurate. Okay, so this is the model that you need. And if I just stop right there, you should be able to do the trigonometry. So the total height of this triangle is whatever this distance is plus 1 foot. Okay? So we don't know what that is, but whenever we find it, we're going to add a foot to it, and that'll be our total height from the ground. All right, so let's put this right here, which I'll draw in red. This was our red dot that you saw in that picture. Okay? And that picture, I'll just show it one more time. Right there. Our red dot. But you know, I didn't know that 6.25 feet. I didn't know that at the time. I was going to find that. So we'll see what I found using my instrument right here. So I'm going to use this to find this height right here. Okay, well, how will I do that? So I paced off 10 feet. I took an angle. I got 27 degrees. And now what? Well, here's what we're going to do. I'm going to zoom out a little bit on this camera, if I can. All right, so now I've got my model. So, ladies and gentlemen, I need to find the sine of 27 degrees and the sine of 63 degrees on a unit circle. Now, this is a method that's different than you're probably thinking of a way, hey, I could plug something into a calculator really quickly. But I'm saying that we're going to do this by hand. All right. So far, I think you'll agree that there is nothing in this construction that an ancient Egyptian or an ancient Sumerian or an ancient Greek or any ancient person, Pythagoras or whoever built the Great Pyramid, there's nothing there that they didn't have available to them. A leveling device, a protractor with an arm on it, and a distance that they knew, some measurement that they knew. So we're trying to act like we are in the Stone Age and we don't have anything really complicated available to us. So we know we're going to use our unit circle here to find the basic measurements for an angle of 27 degrees and 63 degrees. So the very first thing I need to do is draw a unit circle. There's a unit circle, and I'm going to mark off, normally I would do this using the sacred geometry methods, but I'm just going to mark off some points here to make things a little bit quicker. I'll use my cheater tool to approximate 90 degrees. This little dot right here, make it a little bit bigger. I'll put the protractor right on the center of the dot and put little marks off to the left and the right. All right, and then that will bisect the triangle. That will cut it in half, or the circle cut it in half, just like that. All right. All right, now I need to do the same thing one more time. My midpoint was right here. So find the midpoint. Side in 90 degrees. Put your little dash marks to the left and right. And you can cut this triangle, or cut the circle one more time. I don't know why I want to keep calling it a triangle. Okay, now, ladies and gentlemen, you have a unit circle. The hypotenuse or radius of this circle, the radius of this circle, as we know in unit circle, this is a unit circle. Okay, in a unit circle, the radius equals 1. Okay, and in our example, we're going to be talking about feet, but right now, unit circle of radius 1. So now, ladies and gentlemen, I just need to side in 27 degrees here. One more time, 27 degrees, because that's the angle I sighted. There's 20 degrees, there's 25 degrees, 26, 27. Protractor goes back in the middle of the circle. Line up your axis correctly, and then make a little mark. See right here? Make a little mark where this passes through 27 degrees. See that mark? Now you're going to kind of connect the dots. Oops, I was doing it all wrong. I'm trying to make this show up well for the camera. And then you're going to drop, if you drop a vertical right there, you'll have the sine or height of that right triangle at 27 degrees. So this right here is 27 degrees. I just want to sharpen this pencil up a little bit. All All right, so this guy right here is 27 degrees. And that's a right triangle. So things are getting small, but we'll be okay. So now, ladies and gentlemen, how do we find what is the height right here? What is that? And what is the base? Not to the edge of the circle. We know that. The hypotenuse, can you agree with me that the hypotenuse, if I just, that's also the radius? It's a radius of circle 1. That's what a unit circle means, radius of 1. The hypotenuse of a unit circle of 1 is the radius of the circle. So this we know. We know this is 1. So we're going to use that. We're going to use that. Let's go over here. Let's take a little trip to this side of the page. So let's go up top. Here is my, we'll call this my unit circle. Trig. Okay? All right. So first, ladies and gentlemen, first we need to find 27 in radians. Now that radian measurement is a portion of the circumference that is inscribed by the arc of 27 degrees. It's that arc right there, the arc. It's a portion of the total circumference of the circle. Right? So here's what we're going to do. Since the total circumference of the circle is 2 times pi times r, which is 1, so it's just 2 pi, the radian measurement of this portion of the circle inscribed by 27 degrees is found by multiplying 27. There are 360 degrees in a circle, keep that in mind. 27 times 2 times pi all over 360. So the question is, can this be reduced? Sure it can. We can divide a 2 out of both these numbers, right? And that will leave us with 27 over 180 times pi. But I think we can also reduce down more. We could divide a 9 out of the numerator to get 3. And we could divide a 9 out of the denominator to get 20. So the way we would write this radian measurement for the arc formed by an angle of 27 degrees on a unit circle is 3 pi over, ladies and gentlemen, drum roll, 20. 3 pi over 20. That is the radian for 27 degrees on a unit circle. It's important we put unit circle. Okay, and I should say like of radius 1. Of radius 1. I don't need to write that every time, but it's important you remember when you just see 3 pi over 20, we're talking about a unit circle of radius 1. That becomes important in a moment. So this is for 27 degrees. Now we need to find the other angle, which we said was 63 degrees. So let's do the same thing for 63 degrees. 63 degrees. That's just equal to 63 times 2 times pi over 360. Well, 63 times 2 is, let's see, 126. Okay, 126 divisible by 2. We know we can pull a 2 out of the numerator and the denominator. Let's see what we get. This reduces down to 63 over 180 times pi. Now, can we reduce 63 over 180? Well, I believe we can. We could pull a 9 out of both of these terms. Let's pull a 9 out of 63. We're left with 7. Okay? 7 times pi. Now, pull a 9 out of 180. What do you got? 7 pi over 20, right? Because 180 divided by 9 is 20. Okay? And this is the radian for 63 degrees, right? On a unit circle of radius 1. Right, so I'm not going to write all that out. I think at this point it is useful to compute the actual radian measurements. So here's what we're going to do. These are going to be our, I'm going to do this in pen so it shows up really clearly. These are our radian measurements. All right, my pen might be running out of ink. All right, let's start with 27. 27 degrees in radians. We said that that was equal to 3 pi over 20. Well, let's approximate pi to 3.14159.265. We'll take pi out there. We'll take pi out that many digits. That'll be useful enough for what we're doing. Okay, so if we're actually going to multiply this out into a decimal form, we need a calculator. All right? So here we go. 3 times, then this number, 3.14159.265 equals 9.4247775, all divided by 20, That gives us a radian measurement for 27 degrees equal to 0.4712388975. Let's do the same thing for 63 degrees. We said that equaled 7 pi over 20. Let's multiply 7 times 3.14159.265 equals 21.99114855 divided by 20. And that gives us a radian measurement of 1.099557. All right, let's write the whole thing out. 1.0995574275. Okay? So these are our two radian measurements. We're going to need these values here in a moment. Let's switch back to pencil, sharpen it again. Now we're going to calculate trigonometry values for two circles. First, we're going to do the small circle, this one right here. All right, well, we don't need to do the small circle because it would be ideal to know this distance. We're going to go ahead and find it, by the way, and this distance right here. So we don't know that. We don't know that. We also don't know this distance up here. We don't know that. We can find it, but we don't know it right now. Okay, so let's start with this small circle. This small triangle. You don't have to do this because you already know the height, but let's just do it for the pleasure of doing it. All right, so we know, ladies and gentlemen, we know that on a unit circle, the sine, or the radian measurement of 27 degrees equals 0.4712388975. All right, so in order to find the height right here, but for this one we're doing unit circle height. We're not yet considering our actual, this doesn't exist yet. We're just looking at unit circle. To find that unit circle height, see I've got a little question mark there. We need to just do this. So we're going to say the height here, height on unit circle for 27 degrees equals the sine of 27 degrees. And we express that in this radian measurement. So the sine of 27 degrees, right, we need this radian measurement. So this time I am going to defer to a fancy calculator to do math for me. So I'm just going to put sine 27 degrees because I have this in degree measurement. I'll show it both ways just so you see. I take the sine of 27 and I get 0.45399049997. That's the height right there of that triangle, that right triangle. That's the sine of that triangle. But now let's put this in mode. Let's go back and put it in radian. All right, quit. Now let's do this. Let's do sine, ladies and gentlemen, and then instead of putting in the degree, we'll put in the radian measurement. And instead of putting in this long decimal, we'll actually compute. We'll compute it exactly using 3 times pi over 20. See what I've done there? 3 times pi over 20. Okay? Enter. I got the same thing. Both answers are the same. It's just different modes. You're in degree mode, you're in radian mode. I'm going to go back to degree now. Okay. So this is my height. I'm actually going to write this in now. 0.4539904,997. For a unit circle of radius 1, the sine of 27 degrees, the height of that triangle right here is 0.4539904,997. So we're actually going to write it in up here too. This guy equals 0.4539904,997. I could have computed this using the Taylor series for sine, but this is just much faster. And you can watch that Taylor series approximation algebraically in a different video. Okay, so now what are we going to do, ladies and gentlemen? Well, we're going to compute the base right here, this guy right here. Okay, base equals, I don't know. So let's go down here and say that the base on a unit circle for, now what? Before I write that right there, what am I computing the base of? Well, we're only going to work with sine today. So if I turn this whole paper 90 degrees, then this angle, 27 degrees, okay, 180 degrees minus 90 minus 27, this angle right here is 63 degrees. Okay, fair enough. So the height opposite that angle, the height there is the base. All right, so let me just show you something here. The base on the unit circle for 27 degrees is equal to the sine of 63 degrees, all right, or the cosine of 27 degrees. It's the same thing. I'm referring to that same distance. Whether I'm doing the sine of 63 opposite or I'm doing the cosine of 27 adjacent, I'm going to get the same number, ladies and gentlemen. So we'll do it both ways just so you see. we'll say this. We'll do sine first of 63 degrees. Calculator back on. This time we'll put it in radian measurements, so we see this a different way, just showing you different ways of doing things. So we're going to do the sine of 63 degrees in radians. So I'm going to need this number right here to calculate what I'm doing. So I'm going to take the sine of 63 degrees to get this base up here. The base, which is the height of the 63 degree angle. Right? So I'm finding the height of the angle of 63 degrees. Same thing as the base of the angle of 27 degrees. Think about a triangle for a moment, you'll get it. Oh, I'm doing the inverse sine. I don't want that. I just want the sine of, I've got it in radians, of this number, 1.099557427. 5. Close paren. Okay, what we're going to come up with is 0.8910065,236. Now, let's put that here. .8910065,236. So the sine of 63 is 0.8910065,236. Now, how about this? What's the cosine of 27? Because that's probably what you had been taught to compute. So let's find the cosine of 27, but we're going to do it in radians. So we're going to go back up here to 27. This time we're going to use our radian measurement. So I'm going to say sine, or rather cosine, excuse me. I'm going to say cosine, and this time I'm going to put in the radian measurement for 27 degrees. The cosine of 27 degrees is 0.47123888975. Now what I'm predicting, ladies and gentlemen, is that you're going to get the same number that you got here. There it is. Out to several significant digits, it's the same exact number. All right, so here where this equals 0.8910065,244. Only the last two digits were different on both these numbers, so we'll just drop those. That'll help us find out what our level of precision is. We'll just use this portion of the decimal. All right. Now what? Well, we have found our measurements for a unit circle of radius 1. Now we need to scale up to, first we're going to do this smaller triangle here. We're going to scale up from there. Okay? So what do I know? I know that the height was 1 foot. So if I'm looking at the angle of 27 degrees, I know the sine. All right? But I don't know my scale factor. So here's the setup. Let's go down here. Okay? This is going to be the smaller triangle. All right, so here's what we're doing. We know, ladies and gentlemen, that if we multiply the sine of 27 degrees in radians by a scaling factor that we don't know called x, we will have 1 foot. Okay? That's how that sets up. We know 27 degrees. We know it in radians. It's that right there. And what we're looking for is 1 foot. Okay? So we have a scale factor that we're looking for. We're going to scale up to 1 foot. So sine of 27 degrees, I pointed to the wrong number. Sine of 27 degrees for a unit circle of radius 1 is right here. Okay, we'll need cosine here in a minute. All right, but this is the sine of 27. So here's what I'm going to do. I'm going to plug this in. I'm going to say this. I'm going to say 0.4539904,997 times x equals 1 foot. So if I want to get x by itself, I just divide out this term on both sides. All right? So what I'm going to get is x equals 1 divided by that term right there. X equals 1 divided by, oh yes, I am going to write it out. This is the sine of 27 degrees. That's that height right there. For a unit circle of radius 1, that's that height right there. 1 divided by that height. Okay? 0.45339. 0.4539904,997. What does that equal? Calculator. 1 divided by 0.45399. Oops, do it one more time. 1 divided by 0.4539904,997 equals 2.202689. All right, just write that in. 2.20268926. We'll just go out that far. This is what we're going to call our scaling factor. Okay, we'll call this our scaling factor. All right, we haven't actually found anything yet. So here's what we know. What do we know? We now know, ladies and gentlemen, that the scaling factor for a unit circle of radius 1 for a triangle of 1 foot is 2.2. All right, so here's what we're going to do. We're now going to compute this angle right here, which is 63 degrees. We're going to find this. Here's how we're going to do it, using the scaling factor. We need this guy right here. All right, so I'm still working with the smaller triangle. I'm going to carry this out so it stays clear that we're working with the smaller triangle. Okay, so now we need to find the sine of 63 degrees. The sine of 63 degrees. Well, we already calculated that, didn't we? Over here, we calculated the sine, over here we calculated the sine of 63 degrees or cosine of 27 degrees. Either way, the radian measurement was 0.89100,652 for a unit circle of radius 1. So here's what I'm going to do. I'm going to put a kind of little mark there, and I'm going to say that the base of the smaller triangle equals the base of the smaller triangle equals the sine of 63 degrees in radians times the scale factor of, over here, 2.202 68926. All right, so I've got this information. I've got everything I need. So what is the sine of 63? All right, this could also be the cosine of 27. They're both exactly the same. In radians times a scale factor of 2.202 68926. Well, what is this? We got it right here. We computed it. So take 0.8910065.2. Multiply that by your scale factor of 2.202 68926. And what you're going to get is this distance right here. That's what we're going for. So let's do that. Clear it out. 0.8910065.2 times 2.202 68926 equals 1.9626. All right, whatever. Let me write it out. Equals 1.962610.492. Okay? This is the base. That's the base. All right, so this is the height right here. Over here, we found the height. Well, we already knew the height. The height was 12 inches, or 1 foot. This was to find our scaling factor over here on the left. So we got 1 foot for the height, and over here we have 1.962610492 feet for the base. So I think it's a good time to write that information in. Okay, so now we know this. We already knew that, so this becomes 1.9626, we'll just stop there, feet. Okay, fair enough. Let's move on to our larger triangle. Oh, I'm sorry, we'll go ahead and compute the hypotenuse of this triangle. So, ladies and gentlemen, hypotenuse of smaller triangle. That's what we're going to do. Hypotenuse of smaller triangle what that equals is a squared plus b squared equals c squared. All right, well, we know a and b. So we know that if this is a and this is b, we know that a squared is 1.9626 squared plus b squared that's 1 squared equals c squared. All right, so let me square this number times 1.962610.492. That equals 3.8518. All right, whatever. So this is going to be 3.8518 0.85183994368 plus 1, because 1 squared is 1, equals c squared. All right, so the square root of c and the square root of this, I'll just add 1 to this, right? And I'll take the square root, and I get 2.202689. Something should be jumping out at you. 2.202689. Where have we seen this before? This is our scale factor. So the hypotenuse was the scale factor. Let's go ahead and erase this and write it in. That's 2.202689. All right, feet. Everything's in feet. Okay, so now it's time for the larger triangle. And we will make room for our math. Just want to make it clear what we're doing and what we're not doing. All right, so here's going to be our larger triangle. All right, just take it slow, take it easy. Our larger triangle, ladies and gentlemen. So what do we know here? Well, we know the distance, which you would say is the cosine of 27. But well, let's say I don't know cosine. If I turn the triangle this way, I say that this distance now is the height, the sine of 63, or the cosine of 27. So here's how this works. The sine of 63 degrees or the cosine of 27 degrees for a unit circle of R1 of radius equals 1 okay, in radians, multiplied by x, which we don't know, equals 10 feet. All right, so all this nonsense right here for a unit circle of radius 1, the sine of 63 or the cosine of 27, that is just equal, ladies and gentlemen, to the base that we calculated down here. 0.891. I never wrote it in. This was 0.8910065. All right, so that is the base of unit circle. The base of unit circle for 27 degrees, which is equal to the sine of 63 degrees, or cosine of 27 degrees, right, in radians is 0.8910065. So we'll bring that back up here. That's what I asked for, the sine of 63 or the cosine of 27 for a unit circle of r equals 1, radius equals 1 in radians, times x equals 10 feet. Well, that number that this whole thing represents, right, that whole thing right there represents this number, 0.8910065. 0.00652. All right, times x equals 10 feet. So let's isolate x by itself. We just divide out this and divide out on that side as well. Divide 0.891 or divide x by 0.891000652 and then divide 10 by the same thing. So we divide 10 by 0.891000652 and see what I get for x. Take 10 and then divide out 0.891000652 and I get 11.22. Wait, getting the wrong number here. I think I did that wrong. Let's just do this one more time. 10 divided by 0.891000652. All right, 11.22. 3262491. All right, remember this again, ladies and gentlemen, is our scaling factor. This is a scale factor. We haven't gotten to our number yet. Okay, so now what I need, ladies and gentlemen, is to find for this larger triangle what the height is. All right, so I knew this. This is what I knew. I exploited what I knew. Now I need to find what I don't know. So here's how you find what you don't know. We knew the sine of 63 and the cosine of 27. We already knew that. That multiplied by some scaling factor. We took the radians for that of a unit circle of radius 1, multiplied it by x, and that we knew that equaled 10 feet. And we found the scaling factor from radius unit 1 to the radius of whatever circle is made by this triangle, this bigger triangle right here. So now what we're going to do is say that the sine, this height here is equal to the sine of 27 degrees. Okay? So we're going to say the sine of 27 degrees in radians. I think it's important to always point out when we're doing radians. Okay, multiplied by our scaling factor of 11.2232624291 will equal the height, okay, of the larger triangle. That's what I'm predicting. Okay, in feet. So here's what we're going to do. We're going to calculate this out. The sine of 27 in radians times 11.2232624291, that's the scaling factor, is going to equal the height of the larger triangle in feet. So what was the sine of 27 in radians again? Well, let's go back down to our calculation. The sine of 27 in radians is 0.47. Let's get both of these in frame so you can see. I'm going to transpose this number up here. I'm going to say this was equal to 0.4712388975, all right, times 11.2232624291. Let's just do that multiplication out, and we'll have the height of our larger pyramid. We're going to have this distance right here, which was just equal to the sine of 27. So let's multiply that out. 0.47123888975 times 11.2232 624291, and that came out to 5.28883781344. All right, feet. That is this height right here. So why don't we round to the nearest, I don't know, couple of digits. We'll call it 5.29 feet. We'll say 5.29 feet. That's good enough. All right, so 5.29 feet. And now remember, we're not quite done yet. That was the distance of the red dot, okay, to where I was looking at it from my eye. But now I've got this extra little 12-inch space in here. Well, this is 1 foot. So down here, if I take both of these together, I've got 6.29 feet. This 6.29 feet is the height of the dot to the floor. So let me label that. This right here is the floor. All right, so from the dot to the floor is equal to 6.29 feet. Now, what was my actual measured distance, ladies and gentlemen? The actual measured distance was, let me write that in a different color. So we're going to call this here our calculated, here, we'll call this will be our little results part. This is our calculated height. And that was equal to 6.29 feet. Okay, calculated height 6.29 feet. Now, how about the actual height? The actual height, measured with a tape measure after the fact, the actual height was equal to 6.25 feet. Okay, pretty remarkable. Guys, I was using an instrument this crude to do my my sightings with my the sightings that I did by looking through using a straw and a compass and a ruler and a level, laying on the floor, all right, pacing off using my shoes as the measuring tool. I came up with a calculated height of 6.29 feet where the actual height was 6.25 feet. I want to double check that. Yeah, 6.25 feet. So what was my margin of error? Here's my margin of error. The way you find margin of error is you take your calculated height, we'll say margin of error here, margin of error equals, and ladies and gentlemen, this is amazing. It's amazing that we were able to take a crude instrument like that and actually compute trigonometry. And here is all the work. It's all here for you to see. So you've walked through it with me for the last hour and 15 minutes. So let's calculate the margin of error just so we see. That would be equal to 6.29, the calculated height, minus the actual height of 6.25 feet, all divided by the actual height of 6.25 feet. times 100 to get as a percentage. So let's do that. Let's do that. Ladies and gentlemen, 6.29 minus 6.25 equals 0.04 divided by 6.25. That equals 0.0064 times 100. 0.64%. So the margin of error was 0.64%, not 64%, ladies and gentlemen. I want to make this decimal point really big. 0.64%, not even a percent off. So the amazing thing, I think, is we take away from this image, I'm going to zoom out again so you can get a complete picture of how awesome you are, because I'm assuming you did this. If I zoom out one more time, all the way out, looking at all my cool math that we just did, you did, not just me, right? And here's my instrument that I used, right? Looks pretty cool, right? Now it looks really cool because now we know it works. That let's take a look back at our image. Okay, we now know that the calculated height that we came up with was 6.29 feet. We were off, ladies and gentlemen, by just 0.64% from the actual height, which is remarkable. It's remarkable that we could do that. I threw this thing together in just a few seconds, really, using things around the house. So let me hide that image again. So I came up with, using nothing more, ladies and gentlemen, than a little bit of ingenuity, a little bit of thought. We came up with the height of a dot, a randomly placed dot on the wall, by creating a survey tool using Velcro, a protractor with a rotating arm, a straw that I found thrown outside, a ruler of 12 inches, and a level to make sure that I'm level to the ground. And guys, we're right to within 0.64%, not even 1% off. Then I think, ladies and gentlemen, brothers and sisters, that this is, the best way to describe it is really, really freaking cool. And I hope that you found this interesting. I hope that you found this tutorial interesting. And please like and subscribe, ladies and gentlemen. This is a lot of work, and I appreciate your support. I'll leave this here and let you screenshot that if you want to. This will be posted in the description. A very high resolution image of the work you see here will be posted in the description. If you have any questions about how we could have calculated all of this without even using a trig calculator, like I use that TI-84 plus CE in order to get the radian measurements of the sine for 27 degrees and the sine of 63 degrees, but I didn't need this. I could have used the Taylor series approximation, but I wanted to save time because this video is already running an hour and 18 minutes, and that would have probably added an hour of hand calculations to do the Taylor series. Needless to say, I have other videos where we compute that. We compute by hand using the Taylor series. Okay, I hope you're clapping your hands for yourself. Golf clap for that. You did a very good job here. If you created this instrument, all right, and then you did all these calculations, you have impressed me. Go out and you've impressed yourself. You go out and find the heights of things that you don't know, right? So now that you know your margin of error is 0.64%, you can go cite the top of a flagpole, the height of a sign, a jack-in-the-box sign, the top of your school, the height of a car, whatever you want the height of. And then just pace off the distance by going heel to toe, heel to toe, heel to toe, using your feet, and measure your shoe so you know how far you've gone, and then proceed according to the video that you just watched. So we'll leave it right there. I'm going to leave it just like that. That's really cool. I think it's awesome. Thank you again, and good luck.